I would like to share some thoughts on how we at National Instruments see a convergence of design and test. Over the last years, we've been adding to our technology of LabVIEW and PXI and Compact Rio to extend its use and role from what we've been doing with test and measurement into new areas such as industrial embedded. This new approach allows us to share technology between design and test. In other words, we're able to apply our test technology and design technology in a way that are mutually supportive in what they can do. This relates to how many design processes operate with a dual between system-level design and system-level test on through the component-level design and test onto the implementation itself. And today I'd like to show how that view of test and design can be used to define a new way to do test, adding elements of cyber-physical testing, in other words, real-world testing, protocol-aware test, along with your traditional approach to vector-based tests that typically have been historically used for digital test applications. Looking at the design process as we've seen it, historically, domain experts would define the general requirements for a system, and then a team of hardware and software designers would implement the actual design. At National Instruments, we see an alternative where domain experts can play a bigger role in the process of implementing the system with high-level, system-level design tools, and perhaps assisted by system engineers to look at things like I/O systems and the like. This can then, as we expand to higher volume applications, be mapped into a process for directly specifying custom ASICs and the like to complete the design process. So this new approach, which we call graphical system design, enables a convergence between design and test with system-level test and protocol-aware capabilities. We can deal with some of the key challenges of traditional ATE systems, including such things as the lengthy test development times, poor test coverage, poor early yields because of mismatches of the test, and increasing test times as we have to use special techniques to deal with protocol-aware systems. This in some ways represents a return to system-level test where with time the complexity of systems on a chip are such that the number of pins are reduced, the ability to do traditional pin-based testing is substantially reduced, and this can be bring us back to more approach that had been used in the past of doing system-level tests on board-level designs. In fact, we're living in a world where many components don't even have pins. For example, RFID, tire pressures, energy harvesting devices, smart cards, and key fobs are examples where no pins exist for the testing. This is typically RF communication by RF. And then there are a lot of devices with just a few pins. MEMS devices, tire pressure ICs, RF radios, displays, and audio devices. Each of these now often have protocols for communication with the device, which really restricts the opportunity to make maximum advantage of traditional test ATE approaches. An example is the pinless ATE for RFID tags, where we have to create an RF-based protocol and implement the test without any pins. So we see these as trends of moving from low-level abstraction of the devices to high-level protocol-based abstractions. We see where in the past you may be able to make synchronous communication with the device. Now it's often asynchronous. Pin access may be quite limited, and traditional ATE systems have difficulty dealing with these trends. Here's an example of how a WLAN baseband chip may have been created in the past with digital vectors directly to the baseband onto the analog to digital converters and analog I/O. And this traditional test can work quite well. Moving forward, we see more and more chips with processors on board with asynchronous protocols, making it substantially harder to make these chips efficiently tested with traditional ATE systems. We can now apply our view of convergence of design and test with concurrent design and test, where system-level design and system-level test correspond with our physical or mission-aware testing, our system-level test and protocol-aware test, on to a component level where we may use the traditional approaches for digital pin driver approach with built-in test and JTAG test. Some definitions are in order. Physical or mission mode testing is a technique for real-time system-level testing where we're emulating or working in a real-time, real-world environment. Hardware-in-the-loop testing is about a technique that's used for development and test of real-time systems where we emulate with hardware, perhaps a PXI system, the environment of sensors and actuators that the control unit or unit on a test will be tested with. Protocol-aware tests builds in the ability to now deal with asynchronous protocols, which where real-time is communicated with a specific protocol requiring special techniques for testing. Key features of protocol-aware testing are interfaces are programmable. We can perform real-time state detection, have handshakes with devices using native protocols, and it can operate with numerous interfaces such as memory interfaces, parallel buses, serial buses, RF and audio, and can act as either a master or a slave. This move toward protocol-aware tests can be used in verification validation as it more closely emulates the environment that chip will be used in. So in the past, we may have had benchtop instruments with disparate synchronization, poor synchronization. They may be slow and only signal aware. Now with our modular instrumentation with this new capability, it can be integrated testing with tight synchronization and fast real-time data rates for both signal and protocol-aware testing. An example of enabling IP to the pin where we have a system that combines processing capability with FPGAs and signal conditioning I/O and a variety of IP in software and FPGA hardware that allows to emulate a variety of environments for testing. If you look at it in terms of production testing, historically, traditional ATE systems are moving to where they include protocol-aware ATE and can be used on the production line with this new capability to provide better test capability, faster responses and the like. We can do the same thing with our PXI-based systems where we can do the validation and verification on the test designer's bench and then move on into replacing traditional modular instruments and then move on into production testing. So we see a new approach that's more closely related to the design process where we can include any level of testing in our final production test. So if we discover some particular problem where the chip or design is not working as planned at any level in the design process or implementation and field testing location, we can provide tests onto the factory floor to emulate each of the different situations, all the way from cyber-physical, hardware-in-the-loop testing, protocol-aware testing on into the traditional ATE approaches. With this, we create a new and better way to do tests. Here's an example of high-volume MEMS production test where significant improvements in throughput, cost, size, and power was achieved through using this new approach to testing based on PXI and protocol-aware techniques. So, conclusion, system-level tests with protocol-aware capability brings a number of benefits, including strong correlation with system requirements, fast validation time, improved silicon debug, superior fault coverage, and reduced production test times, meaning faster time to market, higher quality, and more profit.